Hello and welcome to the 33rd lecture in this series. So in this lecture I'll talk about vector fields in the context of differential equations, ordinary differential equations. So let us, so vector fields, ordinary differential equations, which I'll abbreviate as ODEs, integral curves and flows. Let's start with the notion of a, so as usual, X will be a vector field on a smooth manifold M. I would like to define the notion, now I want to define the notion of an integral curve. So intuitively, before stating the formal definition, if we think of a vector field as an assignment of an tangent vector at each point, an integral curve is a smooth curve in the manifold whose velocity vector, whose tangent vector at each point is exactly equal to the vector field at that point. So to state this, first let me define the velocity vector of a smooth curve. Let sigma from an interval AB to M be a smooth curve well. So I want to say I want to talk about sigma prime t. So what I do is I just sigma is a map from this interval AB to this is M. So if I take a point T, this will go to sigma T. Now on this interval I have the standard basis. If I take the point T for the tangent space at this point, I have the usual basis of which just consists of a single vector. So this vector regarded as a derivation is just d by dt. In Rn we have always talked about del by del x1, del by del x2, etc. But if we have just one variable, we can still use the del by del t notation, but the convention is that when it's just one variable we call it d by dt. So I have this d by dt, then I can take the derivative of sigma, act it on this basis vector, whatever I get I call sigma prime t. Sigma prime t is by definition d sigma at the point t of, actually let me call it t naught, just to sort of d sigma at the point t naught of this basis vector, which is d by dt evaluated at t naught. So this is my definition of velocity vector, and it's, of course, it's when we are, the manifold is just another open subset of Rn. This definition just coincides with, so if M is an open subset of Rn, then this definition is equivalent to the standard definition of sigma prime T naught. The standard definition of sigma prime T naught is just you differentiate all the components of sigma and put them together as an element of Rn again, is equivalent to the standard under the usual identifications. Of course, the usual identification amounts to what we have been doing all along. The tangent space to Rn, on the one hand, it can be identified with Rn, and this on the other hand, it is the space of derivations. And so in effect, the derivations at a point on Rn can be naturally identified with Rn, and we have seen that the reason is that there is a frame on Rn. In other words, there is a basis, natural basis for the tangent space at each point, namely the partial derivatives. Using this, one can go back and forth between derivations and the tangent space as Rn itself. Right, with that in hand, then this is the same as the usual one. All right, then in this connection, having introduced this, I should also mention that remark, something which I should have done earlier. Recall that when we started the course, we had a nice way of computing the derivative as a linear map. Suppose the derivative is acting on a vector v. We saw that it could be computed by just by seeing the action of the map on any smooth curve tangent to v, and then taking one more derivative. So same thing holds here. Remark, if f from m to n is a smooth map, P is a point in M, V is a tangent vector at P, then the derivative of f at P acting on V is now with this notion of sigma prime, f composed with sigma prime at 0 for where sigma from some small interval to M is any smooth curve with sigma 0 equals P and sigma prime 0 equals V. Sigma prime, I've used this sigma prime, the velocity vector of a curve, in two places, f composed with sigma prime and sigma prime itself, and based on this definition that I made here. And this is the proof of that the derivative can be written like this is immediate. It follows from chain rule. While the proof is quite trivial, it's still a very useful fact, because the point here is that the left hand side of this equation here makes no reference to any smooth curve. All that matters is the velocity vector v and the smooth map f. The right hand side seems to involve a smooth curve, but actually in reality it doesn't matter which curve you take, you end up getting the same answer, DFP of V. And depending on the smooth map F, one can choose some nice curve sigma so that it's easy to compute the right hand side. F compose depending on F, sometimes one can choose sigma so that F compose with sigma prime is easy to compute. So that's the usefulness of this. So I will just remark, so here proof is chain rule. Well, so now let's return back to now the other main definition. So this is something very general. It has nothing to do with what I defined here, and the subsequent discussion has nothing to do with vector fields. Now let us come back to vector fields. Let X be a vector field on M. So I would like to, as I said, the notion of a integral curve is that I would like to find a curve whose velocity vector in the sense defined here is exactly the arrow which has been prescribed. So in other words, the velocity vector is the value of the vector field at that point. So let's write that as an equation. A curve a smooth curve sigma from AB to M is an integral curve of X starting at P if sigma prime T should be equal to the value of the vector field at that point. Now sigma prime T, as we have defined it, is actually a tangent vector at the point sigma T. So I want something in sigma T, and that thing is X at sigma T. This is the defining property, and then the starting at P amounts to saying that sigma, so smooth curve. So instead of saying okay, that's okay, let me retain that smooth curve. So let me add that 0 is in AB, the interval contains 0. So I want sigma 0 to be P. So one thinks of this T, the parameter T, as time. So initially the curve starts at P, and then subsequently it moves in such a way so that its velocity vector is dictated by the vector field. Actually, it's actually literally equal to the vector field. So it's let's look at an example on R2. Let's take a trivial example to begin with. Let the vector field X at any point P is just a fixed vector V. So I'll start with V in R2 and X at P is equal to V. So in terms of, so if V is V1, V2, then in terms of this, when I write XP equals V, I'm thinking of V as a element of the vector space R2, but as a derivation we know that this is the same as v1 del by del x1 at the point P plus v2 del by del x2 at P. So we should, in the context of Rn, one always goes back and forth between these two viewpoints. A tangent vector as a derivation and a tangent vector as just an element of Rn. Right. So now here pictorially all one is doing is just if this one has a fixed vector v and one imagines that at every point one is putting the same vector all over R2. So it's clear what an integral curve has to be in this case. So if I start at a point P, I just move along the straight line in the direction of V. So in fact, let's check that. The claim is that if we take any point P, look at the curve. This time I can define the domain of the integral curve, which I said as AB here. I can just take to be the whole real line. Let be just the straight line which starts at P and moves in the direction of V. In other words, P plus T times V. Now, if I compute sigma prime T, as I remarked earlier, this notion of the velocity vector of a curve. So in this parenthesis, I've remarked that this definition is equivalent to the standard definition of sigma prime. So I can just use the standard definition here to say that sigma prime T is just V. For all T, but which is exactly x at sigma T. Therefore, sigma is an integral curve of x starting at P. Now, the second example is, let's look at something slightly more interesting. Again, on R2, I look at this vector field x at the point xy is y del by del x minus x del by del y. The partial derivatives are evaluated at that point x comma y. Let x be this. Now let's take the point. Let p equals the point 1 comma 0. So let's say I want to find the integral curve of this vector field starting at this point. So I guess first, actually, in order to guess the answer, one has to. So let's see what it is at P itself. This would be the x coordinate is 1, y coordinate is 0. So what I get here is minus del by del y. So it will be like this. And as I move along, one can check that the vector field looks like this at various points of the circle. So in other words, the circle is automatically tangent to this vector field. The unit circle with center, the origin, is tangent to this vector field. Therefore, we would expect that the circle the nice parameterization of the circle should give an integral curve. So indeed that's the case. So let's take and sigma t equals cos t and then now I want to move in in this direction, so I'll put a minus sign t, and again t I can take to be any real number. So if we compute sigma prime t is minus sin t minus cos t. Now let's see what if we suspect that this is the integral curve. This is an integral curve. I should know what x at sigma t is. So x at sigma t is, well, sigma t is this. So x at sigma t would be, so minus sin t del by del x at sigma t minus cos t del by del y at sigma t. And this is the derivation interpretation of a tangent vector. If we go back to the Euclidean interpretation, then this would be minus sin t comma minus cos t. So therefore what I get here and what I get here, these two are the same. So one concludes that therefore sigma is an integral curve of x starting at this point P. Now notice that this vector field that we had here at the point 0, 0 at the origin, the vector field is just the 0 vector, 0 tangent vector. In that case, suppose I wanted to find an integral curve which starts at the origin. Well, since the defining equation, so my sigma prime 0 would have to be x at sigma 0, which would be 0. So the curve would have to have 0 initial velocity. And in fact, it turns out that it's easy to check that after I discuss a bit connection with ODEs, that the constant, if curve is the only integral curve if the vector field is 0 at that point. So here's an important, in fact let me state it as a proposition. So whatever manifold one starts with and whatever vector field one has, take any point, let P belong to M, then there exists epsilon greater than 0 and integral curve sigma, which is defined on this interval minus epsilon epsilon, integral curve of x, which starts at the point P. That is one thing. The second thing is this integral curve is unique. This meaning that it starts at P. So there's only one integral curve and there's exactly one integral curve which starts at the point P is the content of this proposition. And how does one see this? So this is where ordinary differential equations enter into the picture. So for this, let's use coordinate charts to transfer the situation to Euclidean space and see what happens there. So I start with a chart U phi. Let U phi be a chart containing P. We get a vector field on, so this is the open set what we have been calling U1, and this is in Rn. So we get a vector field on U1 by, so here I want to define a vector field on U1, so I start with a point, let's say x here. So I would like to specify, so I already had a capital X here, so I want to define a new, so instead, in fact, let me call it, just to be clear, let's call it, label this as small y. I want to define a vector field y on U1. So y at the value little y, well, I just use this, since phi is a diffeomorphism, the derivative is a isomorphism, so I can take the derivative of d phi inverse is going in this direction, so this point is y, I use phi inverse to get to phi inverse y here in the manifold or in the open set U. There I have the original vector field x, the value, and then use the derivative of phi to come back here. So in other words, I look at x at phi inverse y, then use the derivative of phi d phi at this same point, phi inverse y, and this is what I defined to be y. Now, so in other words, given a vector field here, I've been able to get a vector field on this U1. I should remark that, so at this stage, it's important to observe that note if you have a smooth map between two manifolds, and x is a vector field on M, it is not possible to get a vector field on N by using the derivative of f. If I had a single tangent vector, if I had a tangent vector on M, then I know that the derivative will give me a tangent vector on N. but I cannot define a vector field we cannot use df to get a we cannot use df and x to get a vector field on n in any natural way. I mean, cannot use, has to be interpreted suitably, but in any natural way we cannot get a vector field on n. And the reason is that if I start with a point here, so this is m, this is n. If I start with a point here, if I want to get a, and I already have a bunch of arrows here at the vector field here. So if I start with a point here, I would like to use one of these arrows to and push it forward by the derivative to get something here. But the problem is, if f is not bijective, then first of all this y may not even be in the image of f, in which case it's there's no inverse image, so I don't know which point to take. And even if y is in the image, the map may not be injective, so there might be several points in f inverse of y. So it's not clear which tangent vector I take to push it forward. So that's the reason. So but this situation changes for a diffeomorphism. If I had a diffeomorphism, I can push forward a vector field like this. And the way I do it is, so notice that I've already used the fact that the map phi has an inverse here. So I'll stop here. In the next class, we'll resume at this point. We'll quickly check that this map, we already seen some version of this. We'll check that this y is smooth, and essentially we can transfer the situation to an open subset of Rn and find an integral curve in an open subset of Rn. Use that to get back an integral curve on the manifold. All right, so let's stop here. Thank you.